I'm also a former coach for the Magsig Middle School in Ohio. I've coached teams all the way to nationals. I've also been a national, a state, a regional, and an invitational event supervisor, as well as on arbitration committees. So I just finished a couple of years as the Maryland State Director, and I now live in Texas. And I think I'm doing one regional, one state, and I'll be sending questions to help out with national this year. So the first question I have, welcome to your team, was from your coach, was determine the force of attraction between two balloons with charges of positive 3.5 10 to the minus 8 coulombs and minus 2.9 10 to the minus 8 coulombs when separated by a distance of 0.65 meters. So the one thing I would recommend is that if you go to my set of slides, number 6, we're going to use Coulomb's law. Sorry, didn't mean for the product placement. I was drinking a Coke Zero before y'all arrived. So Coulomb's law determines the force of attraction between two charges. If they're the same, positive and positive, there'll be a repulsion. If they're positive and negative, there'll be an attraction. If they're negative and positive, there'll be an attraction. And if they're negative and negative, there'll be a repulsion. Okay? Force is given in coulombs, and it's F equals K sub E times Q1 times Q2 divided by R squared, where K is equal to 8.99 times 10 to the 9th Newton meters squared divided by Coulomb squared, and Q1 and Q2 are given in coulombs, and it's very important, R has to be given in meters, okay? Now, keep in mind, much like gravity, when we talk about the center of gravity, there's a concept called center of charge. In other words, if I have a balloon, in this case, I give its position as where the center of charges are. So if I edit in all the charges, what's the equivalent charge and what's the location? Okay. With electrons and protons and atoms, usually they're very, very small bodies. So the center of charge is really usually right dab smack in the middle. So what we've talked about is we've got two balloons about 65 centimeters apart, 0.65 meters apart. So that's like 2 feet apart. And they've got very, very small charges to them. So I've already started working on this on the whiteboard using Coulomb's law. And so hopefully this is readable. I'm going to turn off that light. Let's see if that is readable. Okay, so what you'll notice here is that KE is equal to 8.9 times 10 to the 9th Newton meters Coulomb squared. Okay, here's Coulomb's law, and Q1 is 3.5 10 to the minus 8 coulombs. Q2 is equal to minus 2.9 10 to the minus 8 coulombs, and R is equal to 0.65 meters. Okay. Be careful because sometimes I'll give it to you in centimeters and you have to convert it. So now our force, and I always like to use the units here, is equal to 8.99 times 10 to the 9th Newton meter squared over Coulomb squared. Okay, so that's KE. And then Q1 is 3.5 times 10 to the minus 8 coulombs. And this is minus 2.9 times 10 to the minus 8 coulombs. All divided by R squared, which is 0.65 meters squared. Okay? So if I take out my handy dandy calculator here, and by the way, you do need to know how to use scientific notation. These two numbers multiplied by each other Okay. So that's going to be equal to minus 10.15 Coulomb squared divided by 0.4225 meters squared times 8.99 times 10 to the 9th Newton meter squared. Oh wait, I almost screwed up. And that's times 10 to the minus 16th. Okay? Now, the good news is the Coulomb squared here cancels out with this Coulomb squared. The meter squared here cancels out with the meter squared there. I'm left with only newtons, which is great news because newtons is the force unit I'm looking for. So now I do a real quick calculation. Okay. What's really bad here is that it gave me an answer in non-scientific notation that I've got to convert over to scientific notation. So that's minus 1, minus 2, minus 3, minus 4, minus 5. 2.16 times 10 to the minus, I just want to make sure I got this right. 1, 2, 3. So it's 2.16 times 10 to the minus 5 newtons. Is that the question is that the answer that they had? And they're definitely attracted because this one's negative and this one's positive. And remember, opposites attract. So team, did you get the same answer? Did you get the same answer? And does it make sense? If somebody could please type. Now you'll notice I always use the units. That's so that they can cancel out. That's another way to double check your work. So the meter squared canceled out, the Coulomb squared canceled out. You have to make sure that you account for all the units. And if I look at that, 9 minus 8, plus 2, and then plus 1, so plus 3, so that's 12 minus 16. So it generally makes sense. But this is how you solve it. Start with the equation, write this down. Now, the other thing that I always recommend is that if you write all this down and you follow the work here, sometimes, not all the time, but sometimes the event supervisor will give you partial credit. The other thing is, if they see that you made all this, and even if your answer ends up being wrong, as long as your units are correct or whatever, if it's a tiebreaker question or something like that, you'll always beat out the kids who left it blank or just put down the answer. Yes, KE is Coulomb's constant, and it is a constant. Okay, that's a great question. Okay. Are there any more questions on Coulomb's law? Keep in mind, Coulomb's law is a constant force based on how close and how big the charges are. It works almost exactly like gravity, except it's just based on the electrical fields. Okay. What's your next question? Magnetic force field. Very good question. Okay, so And please note that I am still in, so this is all in 6, so it talks about capacitors, and so all of this is division B. If we go to practice number 7, okay, and we talk about magnets for a short period of time, we talk about their attraction and repulsion. The key thing to keep in mind is that with magnetic fields, they are loops, whereas like electric fields are like stars and black holes where they're straight lines, or at least curved lines from one point to the other. Here it's a loop, and it goes out of the North Pole all around into the South Pole. Okay. We talk about the magnetic shapes. But the thing to keep in mind is that what creates a magnetic field is the movement of charges. Okay. And so that's where you get all these things about if you've got current going through a wire, you'll get a magnetic field that surrounds it following the right-hand rule. Okay. Okay. And you can see the magnetic field lines. Okay. You can also do a certain loop of a current and create an electromagnet, okay, which has a north and a south pole. And again, you follow the current, the movement of the electrons, and you go around, and that's how you know your thumb points out in the direction of the North Pole, and it goes around. And if you do multiple loops, okay, you can create a solenoid or a more powerful electromagnet such that every time you turn it around, it's like getting a free magnet, if you will. The other thing you can do is you can put some sort of magnetic material in here to strengthen the magnetic field here and make it an even more powerful electromagnet. Okay? But remember, it's the movement of the charges. You have to have current to create the magnetic field. And let's see. But what you're talking about is the Lorentz force law. Okay? So if you look at the Lorentz force law, okay, what it says is that on every particle, you can sum up the forces based on the electric force and the magnetic force. Okay? So Q times E is equal to your electric force. And then Q times V cross B is your magnetic force. Okay? This is one of both of these are good equations to keep. Couple things to keep in mind. Now, mind you, this is practice number 7. Okay? So the force of you'll notice they have these little lines on the top of them. That means they have a direction. So the direction of the force of the electric force is in the direction of the electric field. So if the electric field is going up, that's the electric force direction on a proton. If it's going up and you have a negative charge, like with an electron, it would actually be going down. So you do have to keep track of that. Now, the cross product is sort of for lack of a better term, that's a higher mathematical concept that we'll just now go over. Okay, so you'll look at it this way. I want everybody to make a karate chop. Okay, make your hand flat like this. And then what I want you to do is I want you to just have 2 fingers up and a thumb like this. And you're going to put your middle finger going perpendicular to your index finger like this. And you're going to put your thumb this way. And if you think about it, all 3 of these appendages right now are pointing in 3 different directions. Okay? Okay? So if my index finger is pointing in the X direction, then this is the Y direction. Okay? And the Z direction is right out your thumb. Only works on right hands. That's why they call it the right hand rule. Okay? So remember, X, Y, Z. Make sense? Does that make sense? Is everybody doing this? Super. Okay. So a cross product is where you say, if I've got a charge and the velocity is going in the X direction and the magnetic field is going in the Y direction, the magnetic force is going in the thumb direction. Okay? Because they're perpendicular in 3D space. And the term we use for perpendicular in 3D space is orthogonal. Okay? It's a fancy way of saying perpendicular, not just in 2D space, like when you're drawing it on a paper, but it's perpendicular in 3D space. Okay? So there has to be movement of either the charge or the field. It's almost always the charge, though, in these problems, but it's relative motion. And that motion has to be perpendicular to the direction of the field. Okay? And so once you know which way the charge is moving, okay, like let's say the charge is moving this way. Okay? Excuse me. Let's say that I'm using my right hand. Let's say the charge is moving this way. And the magnetic field is down. So I got a proton that's going this way, and there's a magnetic field that's pointed this way, pointing down. The force will be right towards me. Or let's say I've got that same proton going this way, and now the electric field is up. Okay? I'm trying to get this. I know it looks awkward. So the force now is away from me. Okay? Now, why do I keep saying a proton? Because a proton has positive charge. So you remember in that mathematical equation, QV cross B. So if Q is positive like a proton, this makes sense. If B is positive, this makes sense. Okay. If they're one of them's negative, okay, you can either do it with your left hand or you do all the calculations and then say it's the exact opposite. Okay, so if I've got an electron going this way and it's going that direction and the magnetic field is pointing down, it's an electron. So my thumb points towards me, so the electron's actually pushed away from me. Adriana, no, I do not mean cross. I do mean cross. I don't mean times. Cross is a special form of vector mathematics, which means that you're only going to take the parts when you're multiplying. Sorry, Preston. Don't worry about it. By the way, please don't share any personal data on this at all. But Mr. Zoder, basically what's going to end up happening is that cross means that everything is perpendicular to each other. Now, here's the funny part. Let's say I've got an electron moving this way and a magnetic field that is not perpendicular. It's right in line with it. Then the answer is zero. Or magnetic field. So if let's say I got an electron that's not moving, well, V is equal to zero. Or an electron that has no magnetic field, well, B is zero. Or if V and B are not pointing in a perpendicular manner. Now, we've talked about it when they're parallel. We've talked about it when they're perpendicular. When they are at an angle to each other, you're given the angle, then you take the cosine of that angle. Okay. So the sine of that angle. You take the sine of that angle. Such that if they're perpendicular, it's 1. You multiply the answer by 1. If it's exactly, if they're pointing in the same direction, in other words, it's moving in the same direction as the magnetic field, it's going to be 0. And so a lot of the questions are, you have no magnetic field, obviously the magnetic force is 0. You have a magnetic field, but it's pointing in exactly the same direction as the velocity. The answer is going to be 0. You have a magnetic field, but the charge isn't moving. The answer is 0. Okay. So just like we talked about how current moving charges can induce a magnetic field, a moving magnetic field can induce the movement of charges. And this was part of what gave rise to Ampere's law. It's actually a fairly involved theorem. Normally, I only put that on state test because it's very hard to think about it in terms of 3D. And so, again, you have to know the velocity, you have to know the direction of the magnetic charge, and then you have to know how much charge there is. Well, normally what they'll do is that they'll describe a situation like they'll say a proton is moving from left to right on your paper. Okay, and you draw the little circle with a pus in it, and you know that the charge of a proton, which by the way this should be on in your binder, is 1.6 times 10 to the minus 19th coulombs. Okay, really low charge. Okay, and then they'll put a magnetic field on it. Okay, and they'll say, well, if the electron's not moving, what's the force? Obviously, it's 0. Don't even need a calculator. Okay. However, then they'll say, okay, it's moving 1,000 meters per second. Okay, and it's moving this way, and let's say the magnetic field is up and down. Okay, so now what I do, the electron's moving this way, the electric field or the magnetic field is moving up and down, but it's an electron, so it's actually going to push it towards me or into the paper. Okay, and that's the whole thing. They'll usually ask, is it going into the paper or out of the paper? Be very careful if they say it's an electron, because remember, it's got the negative sign. If it's a proton, it's real easy. The other thing they'll do is that they'll ask the same question with an electric field. They'll say, I've got an electron moving and I put an electric field. Is there a force? Well, absolutely. It's just the electric field times that charge. And the way you think about it is that a proton or a positive charge will move with the electric field. A negative charge will move against the electric field. So whether I got a proton or electron, it will move it up or down. And that's how the old televisions, CRTs, used to bend the electrons back and forth. They would create a really, really, really powerful electric field, and they would launch electrons, and then they could steer them up and down by changing that electric field. Okay. It's a little bit easier because, again, you don't have to take velocity into account. And so even if the electron's not moving and I put an electric field on it, I'm going to make it move. Okay. Yes, that's exactly how they did it. And then the front part of the CRT was coated with like a phosphorus type material. And so whenever electrons hit it, it would glow. Okay. And so at first, a lot of the CRTs were what they called monocolor. In other words, they were either on or off, and they would so every pixel would either be on or off. And so that's where you hear about black and white TVs. That's where we got those from. And then when they first came out with computers and computer monitors, they were either green or sometimes orange. Or sometimes if you were like me and I had an old black and white TV, I could hook it up to my TV. And that's how old computer monitors used to work. All right, next question. Or let me know if y'all need more explanation. Okay, acceleration of protons and electrons. Okay, the key thing to think about an electron or a proton, okay? is that as we apply a force on something, okay, we will tend to move it if it can be moved. And electrons and protons, usually, for lack of a better terms, tend to be very small, and they're real easy to move unless they're acted upon by another force. So, generally speaking, hopefully, they will only give you one source of a force. You know, if you look here at the Lorentz force law, you have both electrical force and magnetic force. Most of the time, they're going to give you either one or the other, okay? They'll either give you this part or they'll give you this part. If they give you both, you have to calculate both and then figure out what the acceleration is. But the key thing is that once you know the force, you can easily determine the acceleration because they'll give you a mass. Okay? So, who here knows if I know the mass and the acceleration, what's the force? Who here knows that equation? Please type it in. Very good. Very good. Force is equal to mass times acceleration. So if you know the mass, okay, and you know the force from Lorentz force law, guess what? Force divided by mass equals the acceleration. And generally speaking, that you have the rest mass of an electron and you have the known mass of a proton, or a neutron. Now, the great part about a neutron, since there's no charge, there will be no electrical force, there will be no magnetic force because the Q is always zero. And so if it's accelerating due to gravity or something else. Okay. Voltage drop on serial circuits. Okay, so we're going to go back here and we're going to go to hold on a second, I got to find the right practice. So hopefully you know where to find the slides. But if you go to the website, okay, let's see. If we go to the primary website here, okay, this is a national website. I go to Division B events. I go down here to Circuit Lab. We've got all of these here, okay? So let's talk about, if you look here, we talk about lots of different things, but one of the things that we talk about is introduction, okay? And we open this one up. Okay, so this is the very first practice. Okay. And he goes through all the important terms and how to, and remember, you may have to calculate resistance at times, so those are important formulas. So if you think, all right, hold on a second. That's not what I wanted. Here we go. We go to practice number 3. Okay. So if we look here, we go through how to identify batteries, how you can make different kitchen batteries. So let's talk about, if I've got a problem here that's got 3 resistors in series, okay, I want to combine them into a single resistance so I can use Ohm's law, V equals IR, to solve for either I or the V or whatever I'm looking for. So if you have a series circuit, you have 2 or more resistors or loads in series. The current is going to be the same through all of the resistors. By the way, this is the practice number 3. The voltage is split between these resistors, okay? So if you think about a series connection, there's only one path for the electrons to flow. So if I've got 1 amp coming in here, I got 1 amp coming out here, I got 1 amp going through here and coming out there and going through here and coming out there, and 1 amp coming out that way. The electrons have to go somewhere. They can't go anywhere else. And the equation is that you can combine any resistors in series to an equivalent resistance of just adding them. And by that rule, the equivalent resistance will always be more than any individual resistor, okay? And then you can solve for the current if you know the entire voltage by dropping it that way. So that's a series circuit. So an example here is if I've got 3 resistors, okay, 300, 300, 400. So the equivalent becomes 300 plus 300 plus 400 or 1,000 or 1 kilo ohm, such that if I have this battery is 1,000 volts or a kilovolt, then the current is equal to V divided by R, or 1 kilovolt divided by 1 kilo ohm is equal to 1 amp. Okay. Now, here is an easy thing to remember. The sum of the resistors, if they are all the same value, then just multiply them by that value. If I have 3 resistors that are 100 ohms, they add up to 300 ohms. I don't even have to add them up. If I've got 2 resistors that are 300 ohms, that's 600. If I've got 3 resistors that are 300 ohms in series, that's 900. So this can be really helpful to do it quickly so you can do it in your head. Now, parallel circuit is different. You have the resistors. Now they're not in line anymore. They're in parallel, okay? And the current is now split among 3 different paths. Think of it as being a stream that's split among 3 creeks. So if I've got 1 amp coming in here, that 1 amp, I don't have 1 amp going through each of these. I've got 1 amp combined. So this might be 1/3 of an amp, this might be 1/3 of an amp, and this might be 1/3 of an amp, okay? Now, finding the equivalent resistance is a little harder because 1 over the resistive equivalent of this circuit is equal to 1 over R1 plus 1 over R2 plus 1 over R3. As you can tell, that's much harder math to solve. Okay. So the next question is you add the resistance of the resistors to get the total resistance. That's right. Okay. Now, one of the key things when they're in parallel to keep in mind is you look for patterns to make your life easier. So if I've got multiple resistors, if I go back to the example, so let's say I've got 2 resistors, 2 ohms and 2 ohms. So I got 2 ohms here, 2 ohms here. So 1 over R equivalent is equal to 1/2 over 1 over 2 ohms plus 1 over 2 ohms is equal to 1 over ohm. So I take the inverse of both sides and R equivalent is equal to 1 ohm. Okay. So that's pretty simple. Okay. Now, you'll notice if I did it for 4 ohms, it comes 1 over 4 ohms. 1 over 4 ohms equals 1 over 2 ohms. So R equivalent becomes 2 ohms. So the simple thing and the pattern you look for here to make life simple is if resistors in parallel have the same value, R equivalent, the resistance is divided by the number in parallel. So 2 4 ohm resistors in parallel are equal to 2 ohms. 2 6 ohm resistors in parallel are equal to 3 ohms, and 3 6 ohm resistors in parallel are equal to 2 ohms. You'll notice that the equivalent resistance is always less than the smallest when they're in parallel. Okay? So, generally speaking, you try to get it to where it either looks like it's a series or it's a parallel. If it's a series and they're in line, you can add those real easy. If they're in parallel, you can add those. They're a little bit harder. Okay? But look for those special patterns. And if you see those special patterns, it can make life a lot easier. Okay? So one of the things that I'll often do is I'll say, hey, How many are 4 1,000 ohm resistors in parallel? Combine those without using a calculator. I want you to combine 4 1,000 ohm resistors in parallel. Write that in the comments. So each one of these is a 1,000 ohm resistor. They're all in parallel. How's that combine? 250 ohms is correct because I could just divide it by 4. Okay. So let's say I've got 5 1,000 kilo ohm resistors. Okay. And I want to get 1.25 ohm or kilo ohms out of it. I want to get 1,250 ohms of resistance using 5 1,000 ohm resistors. What I do is I put 4 in parallel to get the 250, and I put that in series with the 1,000 kilo ohms. So I combine these to 250, and now it's 250 plus 1,000 equals 1,200. And so you'll notice when you go to the homework generator in, I think it's level 10 homework generator resistor marking. The first part is just identifying resistors. Important to know because those are some of the easy questions that the event supervisors like to give. But the other part is that it really gets into designing a circuit. And usually those circuits are designed by somebody looking at that going, like if I wanted to take 3,000 ohm resistors to make a 1,500 ohm resistance, how would I do that? Go ahead and write it down. I want to take 3 1,000 ohm resistors and make that 1,500. Designing a circuit could be for Division B. I have seen it in Division B. I've written it for Division B. I put it in the hard category. But I usually do it like where they can look at it and try to come up with a reasonable way to do it. So you got 3 1 kilo ohm resistors. So the first thing I always ask myself, put 2 in parallel and the third in series. Absolutely correct. The 2 in parallel give me 500, and then 500 with 1,000 in front. That's why you keep doing the, and by the way, it gets much more complex on the homework generator because we use the standard resistor sizes. There are generally 12 sizes of resistor that they've gone through and done mathematical. They looked at geometrical progression and they said, okay, if I only had 12 resistor types, could they be combined and added and subtracted in certain ways to make any resistance? And so that's how they came up with those 12 sizes. Okay, next question. I hope this has been useful for the teams. Well, hello, parent. I'm a former parent. My son is now a sophomore at Ohio State. He did Science Olympiad for many years, really enjoyed it. Never did this event. I think it was because he didn't want to have me as a coach. My question was, what's the next thing that the teams need help on? And this could be from anybody. I know we got 2 people watching. Or 2 groups watching. So if there's any question from either team. So if we go to practice, what happens when a load stops working? Okay. If I go to practice number 11, so this is practice number 11. Okay. So I go to practice number 11. It includes troubleshooting. It also includes what to do about multiple sources. Now, Kirchhoff's voltage law and the current law, while it is only for Division C that they can ask you questions, it is a useful tool. So if you're able to understand it, it will be able to help you do analysis. We also talk about the different types of switches and the different types of fuses and circuit breakers and dependent sources, superposition. But let's talk about troubleshooting. A lot of your hands-on labs are going to be of troubleshooting. The first question I always ask is figure out if it worked previously. If it never worked, it could be a design error. If it worked before, something probably changed. If it never worked, check the design for any flaws, look especially for open and short circuits. Those are the most common types of errors. In other words, a wire is cut, or we never connected, we never closed the circuit, or we accidentally did something that shorted out the circuit. Now, the one thing that I would recommend also is to redraw every circuit as you can, that in a way that's helpful for you to understand it. If it worked before, check for changes. Number one problem is going to be power, okay? Is the power connected? Is it plugged in? Number one problem of all time is it's plugged in, okay? Are the batteries dead? So if you're allowed to, use a voltmeter. A lot of times, that's the number one thing is I'll hook up a perfectly good circuit with dead batteries and see if they can figure it out. Are the switches set up right? Is it turned on? Another thing that I'll often do, I'll turn the switch off so that the load doesn't work. If I've got a safety device like a fuse or a circuit breaker, maybe the circuit breaker is tripped or the fuse is burnt out, which basically is an open circuit, okay? That's how you fix it. Another common cause of a load not working is that it is burnt out. It's broken. The light bulb, the resistor, or the motor could all be burnt out. Anybody who's ever put up Christmas lights has seen that. Every now and then, light bulbs burn out. And they usually form an open circuit when that occurs, okay? However, another famous one that they'll use is any of your wires loose, or is the light bulb, or is the load itself loose? What I would often do is I would have like a setup where I would have light bulbs in my circuit, and I would have them try to figure out what was wrong, and all they had to do was screw the light bulb in and it would work. Okay. By the way, I used to have a bathroom light bulb that used to do the same thing. It would just work itself loose, and then it would stop working. So then I have to tighten it back up. What you do is you try to figure out the design and draw it out, and then test the design. Make sure the design works. If it used to work and passed all of those tests, you really got to look at the design. Draw it and label it. Write down what the voltage and resistance should be everywhere. So what should be the resistance on the light bulb? What should be the resistance on the switch if it's working, et cetera, et cetera. And write it down on your drawing. Then what I do is I measure the voltage in all those areas and I compare to my calculations. Wherever it doesn't match is probably a good likelihood of where it's going to be a problem. Now, just remember, the reason why I say measure voltage is that voltage is something we usually know real well from our design work, and measuring on the voltmeter really causes no issues. If I measure resistance, okay, you have to make sure that the power source is removed or off, and when you measure it, you got to sort of remove the other parts of the circuit, because remember, if it's a circuit, what can accidentally happen is that I'm measuring the resistance, but it may treat the return part as being in parallel. So a lot of times, if I'm going to measure the resistance directly, I'll want to do that in the removed circuit. Other things, always test the obvious stuff first. Is it plugged in? Is the battery not dead? Is the switch on? The wire's connected? Nothing loose? You can usually tell if it's a series circuit if all the loads go out, all the lights go out. It's a parallel circuit if only one is burned out and the rest stay on. Okay? Remember, you're only going to get voltage if you have both current and resistance. So if it's a short circuit, you'll have voltage equal to 0 because the resistance is equal to 0. An open circuit will have a resistance of an overload, but if there's not another path, okay, you could end up with a voltage there, okay? The voltage across a bunch of resistors in series with no current will remain the same. So think about that. The voltage across a bunch of resistors with no current will remain the same. So the best ways to measure resistance, the best way to measure resistance is to remove the element being tested and test it alone, as we've talked to you. So here we go. So we've got all the lights here, 12 ohms each, were working and stopped suddenly. Okay. What are the obvious things to check? So this is my Christmas lights. It's 6 Christmas lights, each 12 ohms. Okay. There's my switch. There's my fuse. Okay. Everything stopped. Okay. Now, okay. Well, welcome. Welcome, Max. So the tested alone, what that means is, okay, I've got a set of resistors here. If I'm going to measure the resistors, it's actually easier for me to remove the resistor from the circuit and measure it outside if I'm allowed. Sometimes you're not, okay? Or I have to analyze the circuit and make sure it's not forming a return trip any other way. Okay. Okay. Now, in that particular case that we were looking at, all the lights were in series. So it made perfect sense that they all went out. Now they were working and then all of a sudden they weren't working. So the first thing I'm going to check is what, guys? Oh, we'll talk about breadboards next. We'll talk about breadboards. Okay. So let's go back to this series circuit. So first thing I notice is a series circuit. I follow my troubleshooting things. I take my handy dandy voltmeter and do I have 6 volts here? Yes, I have 6 volts here. I measure the voltage across the switch. If it's open, I should have 6 volts. And if it's closed, I should have 0 volts. Well, it's closed, so it's a short circuit. I got 0. Then I go to my fuse. If my fuse is blown, I'll have 6 volts. If it's not blown, I'll have 0. Well, I measure it and it's 0. I measure L1 and it's 0. I measure L2 and it's 0. I measure L3, it's 0. I measure L4, it's 0. I measure L5, it's 6 volts. And I measure L6 and it's 0. And what I realize is L5 burned out. Because what happens is, since there's no current flowing through any of those other elements, the voltage just transforms to wherever the break is. That's why when you flip a light switch off at your house, the voltage inside that light switch is now 120 volts difference from one side to the next. When I turn it on, the voltage is 0, and now the 120 volts is right up there in my light bulb. Okay? Does that help? Now, when we troubleshoot a parallel circuit, okay, which by the way, most of them switch to a parallel circuit because nobody likes all the Christmas lights going off at once. So if we troubleshoot a parallel circuit, okay, all the lights, 12 ohms, so we're using the same thing, were each working but stopped suddenly. Okay? So what are the obvious things to check? It's the same stuff. I check the voltage here, okay, and it's should be 6 volts. And I check it in 6 volts. So the battery's working. I check my switch. Guess what? 0 volts. That's great news. I check right here at my circuit breaker and it's 6 volts. and all of these are 0. Well, now I know my circuit breaker is tripped or otherwise not working. So it's open. But if I check it and it's 0, I should have 6 volts across each one of these. Okay? And generally speaking, you're not going to have all 6 lights go out at once, usually. You can have a voltage spike that blows out every light around, but usually what will happen is 1, maybe 2 will go out at one time. When they all go out, it's going to be a power supply or a switch problem or a fuse or a circuit breaker problem. Okay? Real quick, in this particular case, I've got 6 12 ohm resistors in parallel. What's the equivalent resistance? See who can write it down first. Let's see who can do it. 6 12 ohm resistors in parallel. You don't need a calculator. We were just talking about how to do parallel circuits when all the resistances are the same. Oh, you were close. If they were in series, that's exactly the right answer. 72 ohms would be right if they were in series. 2 ohms is the answer if they are in parallel. Remember, when you put things in parallel, the equivalent resistance is always lower than the smallest one. So we know it's got to be lower than 12. Okay? However, when I put them in series, it's always going to be greater than the biggest one. Okay? And so there you go. Okay. Now, I see that there was a question about breadboards. Okay? Now, go back to the national website. Okay. I'm not. Okay. I didn't realize you were showing your work in 2 steps. I was confused. Okay. So let's talk about breadboards. Okay. No, it's soinc.org. This is soinc.org/circuit/lab-b. So you look at all the resources, and one of the things that it has here is the 2019 circuit and breadboard resistors. Okay. And what you'll notice here is that this is a good one to put in your binder, but it shows you how a breadboard is set up. And so what a breadboard does is that it allows you to take simple resistors like this or other wires and be able to put them into a system. Okay. And I'm trying to get the lighting in here right. Hold on one second. Okay. So what you'll notice is that along the top of the breadboard, okay, there are multiple, the wires are connected along the top all the way across. So what you can do is that if I've got a 6-volt battery, I put it in one of these holes, the 6 volts, and across here would all be 6 volts. And then you got the same thing at the bottom of the breadboard, okay? And it goes all the way across. So when I look at this, along this one's got 2 rows, so I could actually have 2 different voltages across the top, okay? And I usually have, and down here on the bottom, I normally put ground. So this is 0 volts. So I put, if I've got a 6-volt battery or 12-volt battery, I'll put the 6 or 12 volts along the top, and then I can grab that from any place along the board. And then I'll put the negative side over here, and then I make this my default ground, my 0. Okay. Now, the other part is that if you look at here, is that on the middle ones, they usually have 5 holes, and they're all going to be attached here. And then there's a break, and then there's 5 more holes. And this allows me, like if I've got these 2 resistors and I want to put them in series, I can easily put them in series. I don't have to tie them or solder them together. I just, hopefully this comes across easily. So if you'll notice on this particular one, right here in this one row, they're in the same row. So it's the same as these 2 being soldered right together. Okay, so these 2 would be in series. If I wanted to put them in parallel, I could do something like this. Now you'll notice it doesn't matter if I go to the top or the bottom of the 5. As long as these 2 are in the same and these 2 are in the same row here, they're in parallel. But keep in mind, if I jump across this band here, they're not connected. And a lot of times what people try to do, just to make life easier, is that when they draw something out, they try to make it look like the picture. So if I was going to put them in parallel, I might do something like this, where these 2 are attached up here and these 2 are attached down here. It's a way to easily attach materials. And it's not for permanent use. It's usually for setting up and making measurements and making experiments. Okay, I saw Zoder is saying they're trying to communicate with me. How? Okay. Okay, y'all need to wrap up your session. Any other questions? Sure, just stay on here. I think the other team's about to drop off. Well, just put the information right here. Is this available? Yes, it's actually saved, and you can go back and review this entire session. You can also email me with any Circuit Lab questions at geaux15@hotmail.com. The other thing that I would say is that if your team would like to have a separate practice like this again, let me know and we'll schedule something. Tomorrow's out because of the Super Bowl, of course. And, I've been having a standard open forum for several weeks and people stopped attending. So we're doing special sessions like this. Zoder, did you have any more questions? No problem. Best of luck at your next invitational or regional. I know you guys will study hard. Keep working on that binder. Okay, so the national website is www.soinc.org. Take care and best of luck to your team. You might have tried soinc.com, or sometimes people will put SONIC and make it Sonic. All right. Any other questions? So you can download at the national website all of the slides. If you subscribe to this YouTube channel, GEAUX15, then you can view all the videos. And I did a video for all 15 different practices. So with no other questions, I wish you nothing but the best of luck. And please reach out to me if you have any follow-up questions, okay? Take care, everyone.